Oh my god, quantum computing is fascinating, but I sure do wish there was a more intuitive way to visualize quantum circuits.
Wait, haven't you heard of MuqcsCraft?
MuqcsCraft allows a user to drag and drop gates onto a circuit diagram and visualize what is happening inside the circuit. In this example, we have 4 qubits in the circuit, so the state vector is a 16 by 1 column vector, but it's displayed in this example 8 by 2 to save space vertically. We can modify that behavior using one of the many display options. For example, we could disable the wrapping of the state vector and then see it as a 16 by 1 column vector. We can open up other views of the circuit. This is a half matrix view, which shows information about each pair of qubits. We can also visualize the reduced state or the local state of each qubit at the output of the circuit, and also layer by layer. There are several circuits that are predefined. Here's an example of a circuit that produces a W4 state. So by opening up these views, we can visualize what's going on inside. We can see how these control X gates are moving the non-zero amplitudes around the state vector until we finally get this result. Another example of a predefined circuit is this partial implementation of Grover's algorithm, where the first few layers here initialize things. Here we have the oracle, and the oracle in this example is tagging one particular base state, so it's rotating the phase of that particular base state. And then the remaining layers here implement one iteration of the diffuser, and the effect of that is one of the base states ends up with a higher probability than the others. In this case, there are many layers to the circuit, so the state vector looks small. We can make the state vector look a little bit bigger if we play with a few other display options. So if we say that we don't need to see all layers at once and we want scrolling in response to the mouse's position, now we can focus on the layer of interest and see the state vector a little bit bigger. It can sometimes be inconvenient to be scrolling down to the display options here. So another way to see the display options is to click here and see them overlaid on top of the circuit. And that way we can immediately see the effect of different display options on the visualization that's here. There are options to export a circuit. So for example, we can scroll down and open up this set of options, and we can click on this link to export a circuit to Quirk. And here we see the circuit generating the W4 state inside Quirk. Now, not all of the gates export correctly because the gates that are up here are not supported directly in Quirk, but the other ones do export. We can also export to IBM's Quantum Composer. So this link opens up Quantum Composer, and this button will copy the appropriate open quantum assembly code, which we can then paste into here. And by deleting these 2 lines, we can see the circuit appear. And again, not all gates will export successfully because, for example, in IBM Quantum Composer, many of the gates don't support more than 2 control bits. But what can be exported correctly is MuqcsCraft supports parametric gates. Here's an example where we have a poly X exponential gate, which was dragged from here in the toolbar. Over here we have the half matrix, which is showing us a single cell because there's only one pair of qubits. Notice the 2 blue bars here that show us the concurrence and correlation of the 2 qubits. So concurrence is a measure of entanglement, and the concurrence of 1 means the 2 qubits are fully entangled. They're also perfectly correlated. So if we measure the output of these 2 qubits, we always get either 0, 0 or 1, 1. And we see that here in the non-zero amplitudes of the state vector. If I hold down the control key and drag with the left mouse button, I can change this angle, and we see that it changes the correlation of the 2 qubits. We see that in the half matrix. So we go from a correlation of +1 to a correlation of 0, and finally a correlation of -1, which is shown by the red color of the correlation bar. But all the while that I'm changing this, the concurrence remains fixed at +1, which means the 2 qubits are always fully entangled. Here's another example of a circuit with a parametric gate. This time we have a Y exponential gate, which came from here. And here the behavior is different if we keep track of the concurrence and correlation. As we change the angle here, holding down Control and dragging with the left mouse button, we see both concurrence and correlation changing together. By the way, if you look at the tooltip I get when I hover over a parameter, it explains how to change this parameter. So I was using the Control key to smoothly change the parameter. I could also use the Shift key. So if I hold down Shift and drag with the left mouse button, now the parameter snaps to nice values. Okay, so again, in the previous circuit I showed, we had only the correlation changing, not the concurrence, which was fixed at 1. In this circuit, both of them change together. And if I modify this circuit a little bit by adding another C0 gate and then change the parameter again, now only the correlation is changing and the concurrence is fixed at 0. So that's yet another case. If you look up in the web browser at the URL, you'll notice that the URL encodes the structure of the circuit in the query string part of the URL. This is the same as in Quirk, and in fact the format used is almost identical. So this means you can bookmark a circuit just by bookmarking the URL. You can also share a circuit with someone else just by pasting this link in an email, for example. Also, the back button in the browser serves as a sort of undo. So if we modify a circuit somehow, we can hit back in the browser and it undoes the change, returning us to the previous URL. There are some buttons we can get to if we click on this. For example, it may happen that you would like to zoom in on part of a circuit. So with Shift right mouse button, you can pan the view. With Control right, you can zoom in and out. And then to get back to the default framed view, we can hit the animated frame button, or we can hit frame and then there's no animation. We can also clear the circuit with this button, and we can go back to the previous state with the back button in the browser. You'll also notice that in the state vector here, the software displays arrows and colors and symbols to help us understand the effect of each gate. But it can only do this if there's only one gate in each layer, and it can only do it for certain types of gates. So for example, in this first layer, there's 2 Hadamard gates. We don't see any colors or arrows or symbols to explain what's going on there. So we could manually move these gates into different layers, and then we see some symbols appear to explain the effect of the Hadamard gates. But another approach we could take is to press the Expand Circuit button, and that will automatically change the circuit so that every layer can be visualized with the colors, arrows, and symbols down here. Certain gates, like this exponential gate, cannot be visualized easily using colors, arrows, or symbols. So for gates like this, when we press the Expand Circuit button, gates like that get replaced with an equivalent sequence of gates that can each be visualized using the colors, arrows, and symbols. So if I press Expand Circuit on this circuit, we end up with this. The exponential gate was replaced with this, and now we can see on every layer the effect of each gate on the state vector.
There's also a button to print out the magic of a quantum state. So if we choose one of the predefined circuits, such as this one, to find out the amount of magic in the output state, we could open up the console and then press this button, and there is the second stabilizer Renyi entropy of the output state, so it's about 3.7.
MuqcsCraft supports several types of coordinated highlighting. If we hover the mouse cursor over a wire, which of course corresponds to a qubit, then in the bit strings down here, we see one particular bit gets highlighted in orange to remind us of the association between bits in the bit strings and wires in the circuit diagram. So the bottom wire corresponds to the leftmost bit in the bit strings, and the top wire is the rightmost bit. If we hover over a particular state vector, then in the circuit diagram we see an orange vertical line segment to remind us of the association between the state vector and the layers in the circuit. We can also hover over a reduced state, and then in the circuit diagram we see the corresponding wire highlighted in orange, as well as the layer highlighted with a vertical orange line segment. And if we hover over a cell of the half matrix, then we see the 2 corresponding wires highlighted in orange. There's also a tooltip that appears with curved arrows indicating the association between the statistics in the tooltip and the bars of the cells of the half matrix. There are also tooltips that appear when we hover over a gate in the toolbar, or over the widgets to expand and collapse different views in the interface, or over amplitudes in the state vector, or over reduced states. There's also support for what we call generalized gates. So a generalized Z, generalized Y, and generalized Hadamard gate. So these are not standard gates, but the reason they're in the interface is that they lend themselves to the type of visualization that we see in the state vector. So their effect is easy to visualize in our framework of colors and arrows and symbols. When we expand a circuit to make the effect of every gate visible, if we check this box, then the generalized gates will be used in the resulting expansion. And this allows the expansion to end up using fewer layers. So it allows for a more efficient expansion. All of the gates in the interface have a corresponding matrix, and you can find the definition of those matrices at this link. So if we scroll down, we can see the matrices for all the gates, including the generalized gates for Z, Y, and Hadamard. It's also possible to open up the console and call parts of the code directly. There is an object called the global circuit, which is an instance of the circuit class, and it has a data member called state vectors, which is an array of instances of the complex matrix class, or C matrix. So let's say we access the first state vector. That's the one that is output right after this layer. So it would be this particular state vector. If you look inside the definition of the C matrix class, it has a method called toString for pretty printing of the matrix. And we can print that out with a call to console.log. So we see that that particular state vector has two non-zero amplitudes, one for the base state 0000 and another one for the base state 1000. We see those two non-zero amplitudes here.